Welcome back, everyone. It's another day, and today we're going to be discussing the concept of a pointer. So, up until now, you can think of how we've been referring to variables as just by their name. We've often said we want to modify the variable named x or the variable named number of apples. So now imagine you have a street of homes. You can refer to these homes in two different ways. You can refer to these homes by the owner of the homes, or alternatively, you can refer to these homes by their address. Similarly, with variables, you can refer to variables in two different ways. One of the ways is what you're already familiar with, is referring to variables by their name, so number of apples, or x. However, another way to refer to variables is by their address. Now, just like in the real world, addresses are going to be unique. No two variables can have the exact same address. Now, you may be thinking no two variables can have the same name as well. However, we found some cases where that is false. For example, you can have two different functions which have two different variables with two different names. However, unlike names, addresses are guaranteed to be unique. A variable's address can only exist if no other variable shares that same address. So what is a pointer and how does it relate to addresses? Just like we have types of int, char, and float, void, all these types, we similarly have a new type exposed to us, and that is the type of a pointer. A pointer type is going to be denoted by the star symbol. And the question then becomes, what can we do with a pointer type? Well, a pointer type is simply a type whose value is an address. So let's take a look at our memory table really fast. So right up until now, we have variable names and variable types and addresses and so many other things. However, we definitely know that the only column in here that can change is the value column. Once a variable exists, the only thing we can change about it is its value. We can't change its type, name, or address, or size. However, we can change its value. So when we refer to variables, the way we search for them is we go through the variable name column and find the variables that match. However, we only look for variables that are in the current function scope we're currently in. So if we have two variables named x that lie in two different function scopes, we would only be looking for the variable named x in our current function scope. So the question then becomes, how are addresses more useful? Well, unlike names, addresses are going to exist throughout the entire lifetime of the program. So if you refer to address 100, it's always going to go to the same place in memory no matter how many times you run the program. It's going to go to address 100. So how do you make a variable equal to an address, especially since we don't even know what address our program starts at? The way we're going to do this is we're going to take advantage of a symbol that we already have available to us. We're going to take advantage of the address operator in C++. The address operator is very similar to a plus operator or a minus operator, so many other things that we've been using. However, instead of any of these things, it allows us to get the address of any variable by name. So all we do is we write this operator, then we write the name of the variable, and the output is going to be a memory address type. Let's try an example. Let's try to write some basic code. Let's use our memory table to predict what the address should be, and then we'll print out the address using this new address operator we learned about, and then see how it goes. So the first thing I'm going to do is write some really quick sample code, short x is equal to 10, int y is equal to 50, and then another short z is equal to 20. And then I'm going to std cout the address of x is, and for now I'm going to print out the value of x, and I'll come back to actually changing it to be the address of x coming up. And I'll do the same things with y and z. Y and z. Great. So in our memory table, what would we get? We'd go ahead and we'd first enter a function named main. And then the type of this function is an int. It has no name because it's a variable. We don't know the value yet. The size is going to be 4 because it's an int. And the address is going to start off being just A because that's where all our addresses start off from. It's some fixed place called A. And then we're going to enter a scope on line 3 And then we're going to make a variable of type short. The variable name will be x. The value will be 10. The size will be 2. Because main started at a and main has a size of 4, the address of x will be a plus 4. Now, similarly, we're going to go ahead and the next line says make a variable of type int. Y value is 50, the size is 4. But because, again, x, the variable x started at a plus 4 and it took up 2 bytes, variable y starts at a plus 6. And then short z, value of 20, size of 2, and now a plus 10, because it's going to be 4 bytes after a plus 6. And then we're expecting to print out 3 statements on 3 different lines. The first line will say the value of address of x is, and we're going to actually print out the value of x, which isn't exactly correct or what we want to do. So we'll be printing out the address of x is 10, and then we're printing out the address of y is 50, and the address of z is 20. But what we really know is that the address of x is some number plus 4, the address of y is some number plus 6, and the address of z is some number plus 10. So the most important thing about all of us is that while we don't know exactly where x is, we don't know exactly where y is, and we don't know exactly where z is, what we do know is y is at the address of x plus 2. X plus 2 gives us the address of y. Y plus 4 gives us the address of z. And similarly, we can also conclude that x plus 6 gives us the address of z as well. So, and by x, I mean the address of x and the address of y over here. I don't mean the values. So how are we going to get the address? Well, we can use this nifty symbol called the ampersand or the and symbol. If we put the ampersand right before a variable name, that's saying get me the address of this variable name. Now again, this might be another symbol that you have to get used to, but eventually it will feel just like the plus symbol where it just means to add things together. Similarly, the ampersand symbol just means get me the address of this thing. So let's go ahead and hit the run button and see what we get. So we get, first of all, remember that these are hexadecimal numbers. We get the address of x is some really large hexadecimal number. Similarly, the address of y is some really large hexadecimal number. And the address of z is some really large hexadecimal number. But if you look even closely, for example, between x, y, and z, you'll notice that they're almost exactly the same. So what is their value? Let's go ahead and look at their relative difference. So the address of x is some number 0x7, so let's write this down, 0x7 f f d d 0c f7 f0 e. And if you look closely, you'll notice that the address of y looks almost exactly the same as that, except instead of 0f0e, it's 0f8. So I'm going to go ahead and just copy and paste this and duplicate it for the address of y. But instead of e, I will be putting down 8. And now we're going to go ahead and do exactly the same thing, but instead of 8, we'll be putting down 6. So this is the address of x, this is the address of y, and this is the address of z. So now that we know that they're all exactly the same except for these, if we wanted to compute the difference between these two, all we have to do is just subtract 8 from e. So if you might remember, e is 14 in hex. So 0xe maps to 14 in decimal. 0x8 is just 8. That's 6. That's 6 bytes. This is 2 bytes. There are probably a couple of questions you're asking here. One, you're probably asking why is our y variable less than our x variable? Why is our z variable less than our y variable? When just earlier we said that y should be 2 more than x. Well, once again, because most people are going to find that adding is easier to write than thinking about something as a subtraction. So in our simplistic model of a memory table, what we do is we add values to be below each other. However, in the real computer, the values are added above each other in memory. So if we think about memory to be a continuous block of things from 0 to 1, our computer adds to the top of it and starts at the very bottom and simply goes up, rather than what we're doing in our memory model, which is we're starting at the top and working our way down. So it's simply a way of phrasing it. So in a computer, you just have to remember that your variables will be before each other in memory, and in our memory model, they'll be after each other in memory. While again, none of this really matters, all you have to remember is conceptually, every variable has a unique memory address. It is useful to know. The next question that really ends up happening is, why is this 6 bytes? We just looked at it. Y should be 2 bytes right after x. Once again, it's because the computer is doing a little bit of magic that we haven't yet discussed. However, I want to show you another example. This just highlights one of the more fundamental concepts of programming. The computer here is choosing specifically to put the variable y 4 bytes further than what you intended it to be at. And there's a good reason for that. Now, what that reason is a little bit more complicated than I'd like to discuss right now, so we'll come back to it later. But for now, you can just assume that the reason they did this is fairly well thought out and well reasoned. I want to show you another example where the computer is going to do exactly what we are expecting. What if I switch the order of z and y? What if I switch the type of y to also be a short? Then what would you expect? Well, you would expect that the variable y is 2 after x, which is then 2 after y is the variable z. Let's see what happens. Well, you can see that x is at ADE, so 0x ADE. Y is at 0x ADC, and then z is at 0x ADA. So what's really happening here? We see that E, remember, is 14, C, if you remember, is 12, so this is correct to only be 2 bytes away, and A is 10, which is also 2 bytes away from C, which is 12. So in this case, the computer did exactly what we expected. The variables x, y, and z are placed 2 bytes away from each other in memory. Now, while all this may seem like a lot, the good news here is you learn 2 things that are really important. One, the specific memory address of a variable doesn't matter. In fact, if I were to run the same code again, take a look. The memory address changed of all 3 variables. And that's exactly why we use the variable a to denote where main is, because it can be anywhere. It's an unknown memory address that you have no control over. But the key insight here is that while I can't know exactly where my variables are in memory, and I can't hard-code a variable that says change memory address 0x7FFF894ABCD, so on and so on. What I can do, however, is get the address of a specific variable and then modify it using the pointer type. So let's go ahead and give that a shot. Now that I can get a variable of this type, now that I can get an address, I should be able to have a variable of the type of that address. Let's see how one might do such a thing. Well, all I have to do, I have to make a variable of type pointer. So, and we can call this xaddr. And the value of this variable will be the address of the variable x. However, a pointer is not nearly descriptive enough, because once I say it's a pointer, the computer is completely lost what it's a pointer to. Not only do I have to know it's a pointer, I also have to know what it is pointing to. So in this case, x address is a address of a short type, or a pointer to a short variable. And let's look at why this is important. Now let's try and fill out this memory table for this type and think about why it's important for a pointer to also have a descriptive type attached to it. So we're going to go ahead and do what we've already been doing for a while and speed this up. Main int no type value unknown size of 4 address of A. We enter a scope on line 3. We make a variable of type short x value 10 to A plus 4 short y, value of 50, size of 2, a plus 6, short z, value of 20, size of 2, a plus 8. And now we get to the interesting one. Now we are going to make a new variable of a type short pointer. It's a pointer to a short type. The name of this variable is xaddr. Now again, just like any name, I can name this variable anything I want. I chose to use a descriptive name, which is xaddr, or address, short for address. And the size of this variable, now this is something new, all pointers, no matter what type of pointer it is, are always going to be of size 8. This is going to live at address a plus 10 because all variables must have an address, and the next logical place for this to go will be 2 after the previous one, which is a plus 8. And now, what is our memory table going to do here? This is really interesting. The value of the variable xaddr is going to be the address of the variable x. So according to our memory table, the address of the variable named x is a plus 4. So I simply set this to be a plus 4. Now this is a really easy way for you to check whether or not your memory table is correct whenever dealing with pointers. The value of a pointer type can only ever be a memory address. If the address column doesn't have it and you have a value here, it's probably not correct. For example, if you set the value of xaddr to be 100, 100 has no meaning because there's no address called 100. The only thing you're allowed to do is have correct addresses in here. So we can do a plus 4. Now, if you go in our memory table and access address a plus 4, you're going to find a short type. And that's exactly why we have to refer to it as short pointer, because it is a pointer to a short type. Now, if you were to not denote this to be a short pointer, how is the computer supposed to know how many bytes you care about at address a plus 4? For example, what if you just had the variable a here? How do you know that this is incorrect? Because a is an address in our memory table. However, a is not a short type. So an easy way for the computer to know exactly what you care about is going to be marking it specifically to be a short pointer. In fact, this is not a convenience. This is something you must do for your code to compile. So now that I have the x address and I have a variable with the value of an address, so what? Why does this matter? What can I do with it? Well, you can do all sorts of things with it. For example, what if I wanted to change the value of the variable at address a plus 4? What can I do with it? Well, I can use the pointer symbol. I can then use the xaddr variable and set the value of this to be 100. What did I just do? The pointer symbol is saying something specific. It's saying go to the memory address that is the value of this variable. And that's a lot to compress, so let's slow down and take it one step at a time. What I'll do is I'll go to the variable at this address. So great, I found a plus 4, and that gives me this address. Confirm really quick that it is the same type. Fantastic. And now, because I do the equals operator, I'm just going to change whatever value is at that variable. So once I have done the pointer symbol on the variable name, what I'm really saying is update the value at that address. So in this case, I've said update the value at memory address of whatever the value of xaddr is to be 100. So I'm going to simply change this to be 100. Let's try again. What if I wanted to print out the value at that address? I can simply just say cout value at. So first we'll print out x address to print out the address is, and then we'll print out. So what did I do over here? I have a line that's going to print out the statement value at, then it's going to print out the value of the variable xaddr. So the value of the variable xaddr will be some memory address. We don't know what it is because we can't predict what a is. And then it's going to print out whatever value lives at that address. So then it's going to go to a plus 4 and print out whatever value lives at that address. Let's try this and see what happens. We would expect that to be 100. Great, it's printing out 100. Now, what else should have changed? If I changed value of x, let's see what happened. What's the value of x? So what would we expect the value of x to be? Well, if we use our memory table, the value of x should also be 100. Is that correct? And indeed, it is correct. So what exactly happened here? Let's try one more. So we'll print it out twice, once before changing the value and once after. Let's see what happens. So a couple of things happen. One, the value of x adder did not change. The value of x adder is still the same. It's going to be a plus 4. And just like in our memory table, the value of x adder did not change. The value of x, however, did change. And again, this is because we're doing something new. We're referring to a variable by its address rather than by its name. And this is a very important concept to wrap your head around, because what you're going to end up doing in many, many code examples is you may not want to have 5 different variables you're passing around all the time. The main value of this is having functions. So let's imagine you wanted a function that would get a user input. So up until now, you've done the following. Int get user input, int y stood cin, y return y. Well, let's take a look at this impact of this code very quick. What did you end up actually do? You would often do int user input equals get user input. So let's quickly write a memory table for this code and see what happens. Well, the first thing we're going to notice is we're going to write variable name none, value of question mark, size of 4, address of A, scope, enter a new scope on line 9, int user input. So far the variable is unknown, it's of size 4. We're going to put this at address A plus 4. Then we're going to enter a new function called get user input. This function is going to have a type of int. It's additionally going to have a, it has no variable name, the value is unknown, the size is 4, it's going to live at A plus 8. Then we're going to make a new variable, int y, the value is unknown, size of 4, A plus 12. And then we're finally going to fill it in. Let's say the user entered in 20. Then we're going to return y, and return y is going to take a look at this thing. It's going to set the value of this guy to be 20, and then it's going to cross out y. And then we're going to jump back out of the function. We're going to change the value of this guy to be 20 and cross this out. So what did we do here? We did a couple of things. One, we had to create 3 ints to actually get a variable filled in. We had to copy that value 2 times because we copied 20 from once from y into get user input and once from get user input all the way up until user input. Let's see how we can do this with pointers. Well, instead of passing in the value of user input, I can instead pass in the address of user input. And this will be a void function because now this time we won't be returning any void pointer get user input. And what is the argument into this? Well, if we look at what we want to do, we want to send in a pointer. So the first thing we know is that this is a pointer. And what type of pointer is it? It's an integer pointer. And what are we and let's give it a name. We'll say user variable. And all we have to do is to cin, fill in the value at user variable. So notice I don't want to change user variable. I want to change the value at whatever lives at that address. Once again, a lot to wrap your head around. So let's try again. Let's make another one. Okay, so let's go ahead and start writing code for this. Same as before, it's going to be main int question mark. For A, we're going to enter a new scope on line 13. We're going to make a variable int user input. The value is unknown. We're going to have a size of 4, and this will live at memory address a plus 4. And then we're going to get to the interesting part. Line 15. Line 15 says, enter a new function. So let's call it pointer user input. So I'm going to shorthand it so it's slightly easier to write out. This function has no type. It is a void type. It has no value. It has none of these things because it's void. We're going to then have some parameters in here. The parameter in here will be int a pointer. The parameter name is going to be called user variable. The size is 8 because it's a pointer type. And this will live at a plus 8 because a plus 4 gives me a plus 8. And then what's the value? Well, the value is going to be the address of the variable user input. Well, the address of the variable user input is going to be a plus 4. So let's go ahead and pencil that in. And then I'm going to go ahead and go into this function. And what does it tell me to do? Well, it says in stdcn, update whatever lives at the value of the variable user variable to be from whatever the user types in. So we go, because again, there's a pointer symbol here. So update the value of the variable, whatever lives at a plus 4, to be whatever the user input says. So let's say the user says 20. So I'll go to a plus 4. Now it doesn't matter that this is out of function scope, because whenever you're dealing with pointers or memory, it doesn't change. It's true for the entire, it's a plus 4 is a plus 4 no matter what program you're running. So we're going to go ahead and update this one to be the value of 20. And that's it. I was able to use the pointer or the pointer symbol to go at the value of whatever lives at a plus 4. And a plus 4 has this value. It doesn't matter what the name is. It doesn't matter anything. All I know is that it's an integer type. And then I simply exit my function. So there's a clear difference in the memory tables between these two. In one, I have to make 3 integers to simply get a value out into my user input. In another case, I just had 1 integer and I updated it directly. This is exactly how pointers are powerful. Pointers allow you to pass variables in and modify them without having to actually not store that result. So why could you not do this without pointers? Well, if we had a void bad get user input
int user variable.
Take a guess. I want you to go and draw out a memory table for this and figure out exactly why bad get user input doesn't do the right thing. Think about it. It's going to be a really useful exercise. And once you figure it out, I think you'll also see the value of pointers. So why are we talking about pointers and why does a pointer type exist? Well, the pointer type is going to open the door for a whole new paradigm of programming. It's going to allow us to do some truly magical things. And honestly, once we've covered pointers, that's it. There's nothing really that new to learn about programming. This is the last fundamental concept, after which everything is going to be purely structural. So we're going to be learning only things that make our code easier to read, easier to organize. But pointers are the last fundamental concept. So once you're able to grasp your head around how pointers work, and hopefully the exercises are going to help enable you to do that, you're going to be ready to start writing effectively anything and everything. This is it. I'm so excited for you. And once again, I look forward to your progress in the exercises and I'm excited to see how you do. All right, until next time, goodbye.